systems of linear equations. So first, let's look at 2x2 systems. So let's review those. So a 2x2 system of linear equations is, well, two equations. So the first equation, say, has the form ax plus by equals c. Second equation has the form dx plus ey equals f. So these two together are called a system of simultaneous linear equations. Let's look at m by n systems of linear equations. So suppose I have a11 x1 plus a12 x2 plus a13 x3 plus dot 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 a1n xn equal b1. And we have, well, that's one equation. And we have, well, m equations. Let's say a sub m1 x1 plus a sub m2 x2 plus a sub m3 x3 plus dot 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 a sub mn x sub n equal b sub m. And so we have here m equations with n unknowns. That's a system of linear equations. A solution to this equation will be a ordered n-tuple, x1, x2, dot, 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 up to xn. And these and this in ordered n-tuple, suppose that it satisfies each equation solution. If, so let me give you some terminology. If we have that this system has at least one solution, then we will call it a consistent system. If it has no solutions, we will call it inconsistent. If it has a finite number of solutions, we will say that it is independent system. If it has an infinite number of solutions, we will say that it is a dependent system. If m is greater than n, meaning that there are more equations than unknowns, then we will call this an overdetermined system. If there are less equations, then we will call this an underdetermined system. Let's recall the techniques that we use to solve systems of linear equations. Graphing, substitution, elimination, the matrix methods, and determinants. Of these, maybe the only one that's will be somewhat new will be the matrix methods. So let me classify systems by looking at how many solutions they have. So first, suppose I just have one solution. And so suppose I have two equations and two unknowns. Then if it intersects at one point, well, that point of intersection is the solution to my system. And this is called intersecting lines, if this occurs. If we have, well, higher dimensions, say like 3 dimensions, and they all intersect at one point, so this point of common intersection between all these planes or hyperplanes, we will call this type of situation intersecting planes. In this case, the system will be called a consistent and independent system. Usually, I will just say that this is a consistent system. If we have no solution, Well, suppose I look at the case where I have two equations, two unknowns. In this case, we don't have any solution, so there's no point of intersection. Therefore, that's the case where we have two parallel lines in the case of having two equations and two unknowns. Or let's say I'm looking at three equations, three unknowns. Maybe we have three parallel planes. Or maybe we have a situation where the planes intersect in such a fashion that we have three parallel lines. Or maybe I have two parallel planes with a transversal plane, and thus obtaining two parallel lines. Situations, but you have the situation where somehow things don't intersect. Not everything will intersect at one point. So this is the case where you have things that are somehow parallel. An inconsistent, independent system, I will usually just call this an inconsistent system when we have no solution. The case of an infinite number of solutions. Well, suppose I have two equations, two unknowns. And so suppose that I have one line and the next line is exactly the same. So this is the case of having two coincident lines. In this case, we say that the solution consists of a one parameter, because it's one dimensional, family of solutions. Let's look at the case of having, say, three equations and three unknowns. Well, I could have that they have three intersecting, well, three coincident planes. So one plane here, another plane here. So they're all the same. In which case, the intersection will be a two-dimensional object. So we'll have a two-parameter family of solutions. Suppose that we have three planes and they intersect all along some common line. So all planes intersect along one common line. Then this will be a one-parameter family of solutions. In general, we will call this a dependent consistent system. Again, usually I just call this a dependent system. So note that a consistent system of n linear equations will have a k-parameter family of solutions where k is 0, meaning they all intersect at one point, 1, a one-parameter family of solutions, 2, all the way up to n minus 1. So they'll have one of these parameter, k or whatever, n up to between 0 and n minus 1 parameter family solutions. So in general, that's what your solutions will look like. So let's do on page 560, problem number 20. Solve each system of equations by graphing. So I'm going to use the very first technique that I gave you. And so suppose I have, so solve each system of equations by graphing. In problem 20, I have equation 2x minus y equals negative 3 and equation 8x minus 4y equals negative 12. Let me call those R1 and R2 so that I can refer back to them. And so let me let's solve for R1 first. So let's try to graph R1. So let's graph the line for the equation R1. So let's graph the line corresponding to the solution of R1. So let's subtract 2x from both sides of my equation. And now let's divide both sides of my equation by -1. And so y is equal to 2x plus 3. So in this case, I have that the slope of this equation is 2 and the y-intercept is 3. Let's look at the equation for R2 and let's try to graph the line corresponding to that. So let's graph the line for R2. So we have the following equation here. So let's look at that. 8x minus 4y equals -12. Let's subtract 8x from both sides of my equation. Minus 4y minus 4y is equal to -8x minus 12. Let's divide both sides of my equation by -4. And so y is equal to, let's see what's happening here. So y is equal to 2x plus 3. Okay, so get another page. So I have that the slope of this line is 2 and the y-intercept is 3. Actually, let's call this the second and the first. Okay, so let's try to graph this. Okay, so the first has a y-intercept of 3 and a slope of 2. So it looks something like this. The second has a y-intercept of 3 and a slope of 2. So they both look the same. So these are coincident lines. So in this case, we have that there are an infinite number of solutions. Let me have another page here. Okay. And so this is a dependent and of course consistent. Consistent, dependent and consistent system of linear equations. System of simultaneous linear equations. I will usually just say that this is a dependent system. Okay, so since the intersection of these intersects along a one-dimensional line, we will get a one-parameter family of solutions. And let's write them out. Well, I can just let a parameter be the x, and then my y has to look like 2x plus 3. Or I can call it some other parameter. Let's call it, say, alpha. And then 2 alpha plus, and this will be for all real numbers alpha. And so, oh, okay, 1 second. And so that is a one parameter. This is my solution to this system. It is a one parameter family of solutions. Ooh, boy, that was long. Let me try to upload. Okay, so what you can, so what I'll do is, oh, this is privately. Now everyone's seen it. Sorry about that. What I will do is I will actually, yeah, send it to me. So send it just to me through email. Then what I'll do is, ask you what time you want to upload it, and I'll have to be after class so I can do it. And then I will allow you to upload it at that time. I'll just make a little change in the thing, and so that when you all of a sudden the test will appear for you again for you to be able to download it. Okay. Let's see. Here you go. See if I can. Okay, thank you. Okay. So, okay, here it is. The next technique that we'll be looking at. So the first technique that we looked at was the graphing technique. Okay. Just doing this was the graphing technique. Now we'll look at substitution. So suppose I want to solve each equation, solve each system by substitution if possible. Problem number 28. 2x plus y equals 3, y equals 5x minus 11. So again, I just call these R1 and R2 so that I can refer back to them. Okay, so first, I want to determine an equation such that it's easy to solve for one of the variables. Well, I look at the second equation, it's already solved for it. So I'll just say solve the second equation for, well, the variable y, because I've already done it. And so I have y is equal to 5x minus 11. Let's call this equation S1. So now, once you have solved for one variable in one equation, you then plug it into the other equation. And so if you've used R2, you must plug your solve variable into R1. And so I'll substitute for y in R1 using S1. So substitute for y. In R1 using S1. Okay, so I have S1, and I'll plug that into R1. And so I have 2x plus y. I'll replace y by what's given by S1. 5x minus 11 is equal to 3. Okay, so I have here, well, 2x plus 5x minus 11 equals 3. Sorry. Combine like terms. So I have 7x minus 11 equals 3. Add 11 to both sides. So 7x is equal to 14. Divide by 7. So x is equal to 2. And so let's call this S2 so I can refer back to it. So now I know what x is. Let's figure out y. Well, I will determine y by using S1 and plugging back in, by using S2 and plugging back into S1 to figure out what y is, variable. So determine y by substituting S2 into S1. Okay, so let's plug in S2 into S1. So I have y is equal to 5x. Let's replace x by 2 minus 11. So y is equal to 10 minus 11. So y is equal to -1. Therefore, our solution is just the ordered pair, well, 2, -1. And that is the solution to my system. So of course, that means that this is a consistent independent system of equations. It's intersecting lines. Okay, so in general, warning, if you solve for one variable using one equation and then substitute that back to the same equation, you'll always look to see, it always seems like you have an infinite number of solutions. And so be sure that when you use substitution, that once you have solved for one of the variables, use it in another equation to simplify. So you can never substitute back into the same equation that you solve for the variable. Otherwise, you'll go in a sort of infinite feedback loop. Now let's use elimination. Solve each system by the addition method, if possible. Oh, elimination is sometimes called the addition method, subtraction method, addition subtraction method, elimination by addition, elimination by subtraction, elimination by addition subtraction method. So if they have any of the words elimination, addition, subtraction, somewhere within the name method, this is all means the same thing. So I may occasionally use differing terms just because it's all the same technique, but it's given several different names. Okay, so here, solve each system by the addition method if possible. So problem number 38. R1, 3x plus 9y equals 9. The next equation is minus x plus 5y equals -3. So somehow I want to solve this system. So the technique is to somehow multiply one or more than one equation by constants so that when you add or subtract, you eliminate one of the variables. So in this case, it looks, well, notice I have a 3 and a -1, a 9 and a 5. 9 and 5 are, the least common multiple of 9 and 5 is much bigger than the least common multiple of 1 and 3. So let's try eliminate x. So the first thing I want to do is eliminate x. So I'll take my first equation, 3x plus 9y equaling 9. I'll take my second equation. If I multiply it by 3, I then get a negative 3x plus 15y equals -9. So that if I add these two equations, I get the 3x's cancel. 9y plus 15y is 24y. The 9's cancel is 0. So let's divide both sides of my equation by 24. And so I get y equals 0. Oh, and I guess I should say this. I'm usually kind of lazy. So rather than writing the solution as an ordered pair, usually I'll just assume that you can write the equation as an ordered pair. And so once I actually have solved for one variable, I'll just sort of box it and say, well, that's the solution for that particular variable. So I know y equals 0. Now, I can now plug into any equation, doesn't matter what, any equation I see up here, so long as it has one variable that's unknown once I substitute for the variables that I do know. And so in this case, I can, let's see, the easiest is probably R2. So let's substitute into R2. So R2 now becomes, when I replace y by 0, negative x plus 5y equals negative 3. And so I have negative x plus 0, negative x, equals negative 3. Divide both sides of my equation by -1. So x is equal to positive 3. And so again, this is a consistent, independent system of linear equations. This is the case of intersecting lines. We have a unique solution, the ordered pair 3, 0. Problem number 54. Here it just says solve each system if possible. So they don't care how you do it. You can do it by graphing, by substitution, or by elimination. In general, you never use graphing to actually solve a system. It's too difficult. So graphing is not really a good technique to use. Second, substitution is usually only used if you've already solved one of the equation for one of the variables. That's not the case here. So the technique that you almost always use will be elimination. Well, of the three that we've discussed so far, it is usually just elimination. And so if I look here, x, y, and z all look as easy to solve for. But what I do notice is that I can eliminate both y and z at the same time. So let's just say I'm eliminating z. So eliminate z. So I'll take the second equation, x plus y minus z equals 0. And I'll take the third equation, x minus y plus z equals 2. And I'll just add these. And so I get 2x, y's cancel, z's cancel, equals 2. So if you happen to get more than one variable eliminating at one time, that's good. And so I've eliminated everything except for x. So now let's divide both sides of my equation by 2. And so x is equal to 1. Now I have to keep doing eliminate z. So I've used two equations. In general, when you do elimination, you have to use every equation in order to eliminate the variables. So I've used two equations, these last two. Now let's use the first and third equation to eliminate z. And so let's do that. So I have R1 x minus y minus z equals 0. And let's add that to R3. X minus y plus z equals 2. So let's add these together. And so I get 2x minus 2y is equal to 2. But recall that y is 0. And so recall that, that x is 1. Recall that x is 1 here. And so I have 2 times 1 minus 2y is equal to 2. And so 2 minus 2y is 2. Subtract 2 from both sides of my equation. And so negative 2y is equal to 0. Divide by negative 2, so y is equal to 0. Okay, good. So now I can plug. So I know both x is 1 and y is 0. I can use that to solve for an unknown, say z. So let's do the following. Let's plug that into R3. Again, I can use any equation so long as it includes just the unknown that I'm trying to solve for. And the other knowns, well, there'll be knowns in the equation. So I have x, which is equal to 1, minus y, which is equal to 0, plus z is equal to 2. So let's try to figure out what the solution is. Okay. And so I have 1 plus z is equal to 2. Subtract 1 from both sides of my equation. So I get z is equal to 1. So again, this is a consistent independent system linear equations. I have 3 planes that intersect at a single point. Use systems of equations to solve each problem. Problem number 82, choosing salary options. For sales staff, a company offers 2 salary options. One is $326 per week plus a commission of 3.5% of sales. The other is $200 per week plus 4.25% of sales. Find equations that express the incomes as functions of sales and find the weekly sales level that produces equal salaries. Okay, so let's try to find the equations. So it says first that the sales, the salary, let's say, the salary, is equal to $326 per week plus a commission of 3.5% times the weekly sales. Maybe I'll call the weekly sales W. Next, the salary is equal to, well, $200 plus 4.25. So this is 4 1/4% of the weekly sales. So these are the equations. Now I want to determine what weekly sales level will give us the same salary. So I'll just set, well, S is equal. And so I'll just set each one of these equal to each other. And so I have 320, let's just write this way, 200 plus 0.0425 W equals 326 plus 0.035 W. Let's subtract 200 from both sides of my equation. So I have 0.0425 W is equal to 126 plus 0.035 W. Let's subtract 0.035. So I get 0.0075 W is equal to 126. And so let's divide both sides of my equation by 0.0075. So W is equal to 1,680. And so a weekly sales level of $1,680 produces equal salaries. Okay, so you get the same amount using either option if you happen to sell $1,680 worth of material per week.